Okay, so this one's not going to be called. This is going to be problem number 3 for the AP Calculus 2023 exam. I just worked out the entire problem and forgot to show you the screen capture on me working out the problem. So I'm going to have to remake the video. So this one's kind of not going to be cold. I will have just worked through it. I hate that, but anyway, it is what it is. So to put this solution on there, I'll try to work it as close to what I did before as possible. We have a bottle of milk taken out of a refrigerator and placed in a pan of hot water to be warmed. The increasing function M models the temperature of the milk at time t, where M of t is measured in degrees Celsius, and t is the number of minutes since the bottle was placed in the pan. M satisfies the differential equation dm dt equals 1/4 times 40 minus m. Time t equals 0, the temperature of the milk is 5 degrees Celsius. It can be shown M of t is less than 40 for all values of t. Slope field for the differential equation dm dt equals 1/4 times 40 minus m is shown. Sketch the solution curve to the point. I didn't open this on Cami because I don't have a printed copy of this. So I'm going to do my best on Cami to sketch the solution field, or the solution on this slope field. And going to the point 0.5, we're going to have a horizontal asymptote at M of t equals 40. So that's about the best I can do with this Cami thing. But on a piece of paper, I might try to get a little bit closer up there to show you that. I'm going to go ahead and go to the non-Cami version. Oops, that's not what it was. I'll have it open somewhere. Maybe that's where I'm going to have to work at. Okay, we'll use the Cami version then. I guess I don't have it open anymore. We're going to use the tangent line of the graph of M at t equals 0 for part B. This is a 2023 AP FRQ number 3. We did part A on the screen there. We're going to use the tangent line to the graph of M at t equals 0 to approximate M of 2. So our function was dm dt equals 1/4 times 40 minus m. And this is going to be the slope of the line when we plug in we're at t equals 0. So we have the 0.05 on the graph. So dm dt, we're going to have the slope at t equals 0. The slope of the tangent line at t equals 0 is going to be check, make sure I did it right. I did, okay. It's going to be 1/4 times 40 minus 5. I'm glad I had to rewrite this because I think I got it wrong the first time. Okay, so this is going to be 1/4 of 35 or 35/4. And so that means that our equation of our line is going to be y minus 5 equals 35/4 times t minus 0, or y equals 35/4 t plus 5. And we're going to use this to estimate approximate m of 2. So m of 2 is going to be approximately equal to 35/4 times 2 plus 5. And I'm going to go ahead and leave it like that just in case. So this is going to be degrees Celsius at time t equals 2. That's my approximation. I'm going to leave that like part A just in case on simplification I would make an error on part B. Sorry. We did the part A was to sketch the solution curve. All right, part C, we're going to find an expression for the second derivative of m with respect to t. And this time we're going to write I'm going to go ahead and write dmdt out just because it's in a polynomial form. That's 10 minus 1/4 m. So the second derivative of that is going to be negative 1/4 dm dt, derivative of m. That's going to be, we have to have it in terms of m, so we're going to replace that. Negative 1/4 times 1/4 times 40 minus m. And again, I'm going to leave that like that for part C. We're going to determine whether it's an approximation, or the approximation in part B is an underestimate or overestimate. So we need to solve this at t equals 2. So d2m, d2. Second derivative of m with respect to t at t equals 2 is going to equal negative 1/4 times 1/4 of 38. That's going to be less than 0. So it's concave down. And since m is an increasing function, and concave down, tangent line is above the curve, close to t equals 2. So the estimate in part B is an overestimate. Now, part D is to use separation of variables to find an expression for m of t, the particular solution of the differential equation. So we're going to divide both sides by 40 minus m and multiply both sides by dt, and then integrate both sides, and we get negative ln absolute value of 40 minus m equals 1/4 t plus some constant. We're going to go ahead and distribute that negative and make this ln absolute value of 40 minus m equals negative 1/4 t plus some constant. Then we're looking for the particular solution. So our point m of 0 equals 5 we're going to use. So m is 5, so ln absolute value of 35 just equals ln 35. At t equals 0, that equals our c. ln 35 is our c. So we have ln 40 minus absolute value of 40 minus m is equal to negative 1/4 t plus ln 35. And when I convert that to exponential form, or that in terms of e, I get 40 minus m. We see that m is always between 5 and 40 from our curve we sketched before, is equal to e to the negative 1/4 t plus ln 35, which equals 35 e to the negative 1/4 t. So if I add m and subtract 35 e, so I get 40 minus 35 e to the negative 1/4 t equals m of t, the particular solution. For m of 0 equals 5. And that's a solution to number 3.